Hello again. This is Math 2232 coming to you from the College page. And the title of this lecture is Some Trigonometric Integrals, Products of Sines, Cosines, Tangents, and Secants. As always, please be an active learner as you watch this video. By way of introduction, consider this integral, which we did in Calc 1. So this is the indefinite integral of cosine x sine to the fifth x dx. Well, we do a u substitution. U equal sine of x. That means that du is cosine of x dx. And so we can use that substitution to get this integral becomes the indefinite integral of u to the fifth du. And we're going to add 1 to the exponent, divide by the new exponent, and reverse the substitution. We find this is 1/6 sine sixth of x plus c. So that integral was easy to do with the substitution because of the presence of the cosine. However, what about the following integral where we've taken this one and dropped the cosine out? So evaluate the following integral, the definite integral of sine to the fifth x dx. You know what to do. Let's see how you did. Now notice that the exponent is odd, so that means what we can do is we can strip out one of these signs. So we're writing sine to the fifth x as sine to the fourth x times sine x. And then what we're going to do is we're going to say that sine to the fourth is sine squared of x whole squared. And then we're going to do the Pythagorean trig identity, cosine squared x plus sine squared x equals 1, meaning that sine squared of x is 1 minus cosine squared. So using this identity, we can rewrite this. We're replacing the sine squared here with 1 minus cosine squared of x. Then we're going to expand this. Now realize when you expand this, this is not 1 minus cosine to the fourth. There is a middle term, and we write the middle term down here. And so now we're going to do the substitution, but this time the substitution is going to be u equal cosine x. So you see we're going to have, this is going to be 1 minus cosine squared, and that's going to be 1 minus u squared whole squared. And when we do the substitution, since the derivative of cosine is negative sine, this negative appears here. And so make sure you understand this substitution. Now we do the calculation. The minus sign remains outside. We expand this. We integrate term by term, getting this. And then we reverse the substitution. So this is our final answer. Make sure you understand each of these steps. And realize that that's going to work whenever the exponent is odd. And I guess I'm saying that again, but notice we were able to rewrite what we did in the previous example because the exponent on the sign was odd. In these cases, all we need to do is strip out one of the signs. The exponent on the remaining signs will be even, and we can easily convert the remaining signs to cosines using this identity. Cosine squared x plus sine squared x is equal to 1. Again, you commit this to memory. If the exponent on the signs would have been even, this would have been more difficult to do, but we could strip out a sign, but the remaining signs would then have an odd exponent, and if you convert them to cosines, the resulting integral would be even more difficult, often anyway, more difficult than the original integral. And so anyway, let's look at another example. So this problem is evaluate the following integral. The integral of sine to the sixth x times cosine cubed x dx. You know what to do. Let's see how you did. Well, this time what you're going to do is, instead of stripping out the sine, because the exponent on the cosine is odd, you strip out a cosine this way. And then I'm going to leave the sine sixth alone, but I'm going to change cosine squared to 1 minus sine squared x, cosine x. And then I'm going to distribute and do the substitution u equal sine of x, and I'm going to use this in my u substitution, and I get this. Make certain you understand this substitution. So this is going to be the indefinite integral of u to the 6th times 1 minus u squared. We distribute, we integrate, adding 1 to the exponents, dividing by the new exponents, and then I reverse my substitution to get this as the answer. 1 over 7 sine to the 7th x minus 1 over 9 sine to the 9th x plus c. At this point, let's pause for a minute to summarize what we've learned about integrating powers of sine and cosine. So we have this, the indefinite integral of sine to the nx, cosine to the mx dx. So if one of them is odd, either the sine or the cosine exponent, we strip out either a sine or a cosine and proceed as we did before. Now, if both exponents are odd, we could use either method. But suppose that's not the case, and by the way, if it is, it's easier to convert the term with a smaller exponent. But that being said, suppose you had an integral that was a product of sines and cosines in which both of the exponents are even. Both m and n were even. Well, then we're almost always going to use these half-angle formulas written in this way. So the cosine squared of x is 1/2, 1 plus the cosine of 2x. This is the sine squared. And we also have this. So these are our half-angle formulas. And the last is called a double angle formula. So these again are committed to memory for application in solving problems. So here's the next problem I'm asking you to do. Evaluate the following integral. The integral of sine squared x times cosine squared x dx, the indefinite integral. You know what to do. Let's see how you did. Now we're going to do this integral two different ways. The first way, what we're going to do is we're going to do exactly what we talked about doing. And so in this one, what we're going to do is we're going to realize that this integral is the same thing as, and I'm using this on both the sine squared and the cosine squared. So this I changed the sine squared x via the double integral formula, and this way I changed the cosine squared via the double angle formula. I do the algebra multiplying this times this and realizing that that's 1 minus cosine squared of 2x. Now you have to continue with this because this is the cosine squared, so this is 1 minus, and again I'm going to use the double angle formula here, or the half angle formula, and I'm changing cosine squared of 2x to 1/2 1 plus cosine of 4x. And then I am now able to do this calculation via u substitutions. Make sure you follow these calculations, but at the end I will get 1/8 x minus 1 over 32 sine 4x plus c. So we had to use several trig identities to do this. Now, it is possible for us to do it a different way by saying that sine x times cosine x is 1/2 sine squared x, and I do this substitution. And this is a second but more efficient approach. You're going to get the same answer. So we use the double angle formula, and again, you should check the calculations, but we get that this is 1 over 8 minus 1 over 32 sine of 4x plus c. Now, this one is simpler in several ways, and so this is a better way to proceed. Also, I could have gotten something that looks different but actually is the same because of trig identities, and so it doesn't always have to look the same if you do this. So seeking in the easiest way to do a problem is good practice. So in general, when we have the products of sines and cosines in which both exponents are even, we'll use those series of half angle and or double angle formulas to reduce the integral to a form we can integrate. And the larger the exponents, the more we'll need to use these formulas, and the problem becomes messier. Now sometimes, in particular in Fourier series, we'll end up with situations where both exponents are even, and we'll run across a situation where the products of sines and cosines have different arguments. So we will have terms that involve sine alpha times cosine beta, or the product of sine alpha and sine beta, or the product of cosine alpha and cosine beta. So whenever we do that, we will use one of these trig identities that you studied in your trig class. Again, these should be committed to memory. These are not going to be provided on assessments. So you recognize this and use these identities. So now I'm going to ask you to please evaluate the following integral. So the integral of cosine of 15x times cosine of 4x dx, the indefinite integral. You know what to do. Let's see how you did. Okay, so we changed cosine of 15x to this, and we change this product, rather, the cosine of 15x times the cosine of 4x. That's going to be the cosine of 11x. That's the difference. And this is the cosine of 19x. Notice the difference doesn't matter because cosine is an even function. And now I just integrate each one of these using trig substitutions, and I get this. So if you were summarizing this, this would be 1 over 22 sine of 11x plus 1 over 38 sine of 19x plus c. In closing, for now, more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. God bless you all. And when I see you again, we'll be doing the same kind of things with tangents and secants.